So first we're going to find out the numbers in the boxes here of Pascal's triangle. And then once you think you've found your pattern, you're going to fill out the 8th row. All right, first box. What number did we find went into here? 5. How many people used this pattern? 1, 2, 3, 4, 5. Yes, good. And you got a 5 over here as well. Did anybody use a different pattern to find the 5? 1 and 4. This 1 and 4, or this, like which ones? Just whichever 1 and 4 you get 5, it works every time. The first two here, the one's right above it, so you're saying that if I take this 1 and this 4, that makes 5. All right. What number goes in here? 15. And this one is 15 as well. How many people did that idea again? Okay. 1 plus 5. Did anybody do anything else? Yes, what did you do? Good. Add 2, add 3, add 4, add 5. Very nice. Okay. Now, do both of those patterns work for the next number? This one under here is 21. Add 5, add 6. Yes, it does. We start always with a 1, then a 7. What do you get for this one? 35, 35, 21, 7, 1. So probably the easiest way is to add the two numbers above to get the next number, but there are some other ways as well. Okay. Now we're going to look at some crazy patterns in Pascal's triangle, but first, where have we seen this idea before? The pathways walking from home to school, that comes up in this, yes. If you ever have seen the Plinko game, where you drop the thing and go ding, 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 and there's different prizes at the bottom. Right now, if you dropped it in the middle one, this is the most likely place it'll land up, because there's 35 pathways to get the middle ones, but there's only one pathway to get to the one on the outside. That's how the game works. There's math in figuring out the probabilities. That's part of it. Useful math. Okay. Just to write a 1. It's always going to start with a 1. Oh, so you would need it to always go this way, right? You just have to get lucky. You have a little bit of, when you drop that first one, you could make it go left or right, by how you judge it. That's physics. Okay. So you would need it to go one way, but you wouldn't want it to go too far, because then it bounces, then you've lost it. You just got to be lucky. Okay. So I'm going to show you some interesting things about Pascal's triangle that are just for interest's sake, and then we'll connect it to what we're learning right now. But first of all, you've seen some different patterns, right? We have +2, +3, +4, +5 to get the 15. I'm going to show you something that you could maybe call the sock identity, or since we're in Canada, we could call it the hockey stick identity. If you make a hockey stick, the numbers in the shaft of the hockey stick will always add up to the number in the blade of the hockey stick, or the length of the sock and the tip of the sock. All right, so that is another way that you could get the 15. And that works for anything. So if I want to get this 20, I could start from the edge. 1 plus 3 plus 6 plus 10 equals 20. We could also add up the numbers in each row. First one's really easy. It adds up to 1. 1 plus 1 is 2. 1 plus 2 plus 1, 4. Tell me when you realize what pattern it is. 8, 16, 32, 64, 128. What are those? They are numbers. Good pattern recognition there. And they're the powers of 2. Okay? So that's pretty cool. If we think of these as numbers, this as 1, this is 11, 121, 1,331, 14,641. What are those? Those are also numbers. There are powers of 11. This is 11 squared. This is 11 cubed. This is 11 5. Now, when you get to row 6, it has 10s in there. But if you started writing 1, 5, 0, carried the 1 over 11, carried the 1 over 6, 1, sure enough, that is 11 to the power of 5. That's kind of crazy, isn't it? It's kind of cool. Okay? How many people have seen these numbers before? Okay, how many people have seen this pattern of numbers before? What's the next one? No. 13. Okay, so you can't say the next one. What's the next one after 13? 21. So whoever said 21 can't say the next one. 34, so you can't say the next one. This is a crazy fascinating sequence. 55. How do you find the next number? You just add the 2 previous ones to get the next one. Do you see it? Okay. It's a famous sequence of numbers called Fibonacci numbers. Okay. Now, Fibonacci is also a guy. I will tell you some stories about Fibonacci numbers if you'd like. Okay. Here we go. How about there? Does that look good? Does that look good? I think that looks pretty good. I like that line. Okay. I like that line a lot. Let's clone it. There we go. So let's go until we hit a number. Bing! What number did we hit? 1 and 1. 2, 3, 5, 8, 13. So if you use that angle, you get all Fibonacci's numbers. Okay, now Fibonacci's numbers, I'll give you the history. They come from idealistic, theoretical rabbit breeding. That's where the Fibonacci numbers started. Rabbit, bunnies, whatever you want. So, Fibonacci imagined this. He said, imagine you have one pair of baby bunnies. Okay? That would mean you have no adult pairs of bunnies, and you would have a total number of pairs of bunnies as to be 1. The next generation, which is what for bunnies, like 2 weeks later, right? How old do you have to be as a bunny to be an adult? Is it like you're born and then a week later you're an adult or something like crazy like that? Whatever it is, the next generation, what happens is the baby bunnies are no longer babies. They're now adult bunnies. And so you have a total pair still of only 1 pair of bunnies. But once bunnies become adults, they have babies. So the next time, okay, and this is Fibonacci had an idealistic rabbit breeding idea that he was not concerned about any kind of rabbit incest. or anything like that. Okay? So, and rabbits will always have a pair of babies, always one boy, one girl, so it keeps working out. So the next iteration, the adult bunnies are still adults, and they have baby bunnies, and so now your total bunnies is 2. The adult bunnies made the baby bunnies. That should be in, that's a different class. And the next time this adult pair has a baby pair, this baby pair becomes an adult. Now you have 2 adult pairs, so you have 3. Now both the adults have babies. This baby becomes an adult, and now you have 5. And it's also idealistic that bunnies never die or get hit by cars, because this was a long time ago that he thought about this. Horses or carts or anything.
One rabbit, create another one rabbit.
They're pairs. Yeah. These are pairs of rabbits. And so the Fibonacci numbers appeared from this idea. 21, 34. Okay. Now, if you just made a theoretical thing like this, and it happened to only happen in one situation, it would be like not very famous. But these numbers start showing up everywhere in nature. Okay? We have the basic model of how a plant grows or a tree grows. It comes out of the ground as a single stem that's weak, like a baby. As it grows, it gets stronger, and once it's strong, it branches off. It always branches off with a strong side and a weak side. And the next time, the strong side branches off with strong and weak, and the weak side gets long. And then this one can branch off, and this one gets longer, and this one branches. And the cross sections, if you continue to do that, model how a plant might grow. Okay? That's not related. So we have it in this. You have it in flower petals. You will have some flowers that have 5 petals. The next size of flowers have 8, then 13. In the sunflower plant, if you look at the sunflower seeds as they go around, you will see a spiral in one direction, and you will see a spiral in another direction. If you count the seeds in one spiral, you will get a Fibonacci number. And if you count the seeds in the other spiral, you'll get the next Fibonacci number. Counted seeds? Yes. Now, if you look at the most typical math textbook, here's a math textbook. Sure enough, it has a plant on there because it's related to Fibonacci numbers. Another famous, what is this? A spiral of a, what animal is that? A rabbit. A snail. So if you start with a 1 by 1 square and then draw a 1 by 1 square, then on this side you could draw a 2 by 2 square, then on this side you could draw a 3 by 3 square, then a 5 by 5 square, and so on. If you start in the corners and spiral, you have the exact shape of a snail and how it grows. So the Fibonacci numbers show up in that. And then if you start dividing the Fibonacci numbers as you get larger and larger. So we start 2 divided by 1 is 2, 3 divided by 2, 1.5, 5 divided by 3 is 1.66, 8 divided by 5, 1.6. You get closer and closer to this number. And this number is sometimes called phi, sometimes it's called the golden number, or the golden ratio. And all of a sudden, or sometimes golden ratio, golden number, golden proportion. And then we start to see this proportion. If you would look at your fingers and how long one knuckle is, how long the next one is, and how long the next one is, and divide them, you get close to this ratio. If you take your height and divide to the height up to your belly button, you get close to this ratio. If it's way far off, you're disproportionate, right? And you've seen people that are disproportionate, sort of like, wow, that person has long legs, short upper body. And it doesn't, right? So we've got these kind of proportions happening all over on the human body as well. And if you take that ratio so that you take a Fibonacci number here and a Fibonacci number there, this is called the golden rectangle. And what's interesting about this rectangle is that if they've done studies where they have the golden rectangle and 5 other rectangles or squares, and they ask people which one's your favorite, they'll all purport, the majority, or it'll always come out that this one's a favorite. And so you've seen this in marketing, right? If you take out your wallet and you look at your credit card, it's in the shape of a golden rectangle. So you're like, oh, this is nice. I should hold this. I should spend this. When you buy stuff in the grocery store, they'll put it in the shape that you'll most likely like to buy it. So cereal boxes don't come in squares. They could, but there's none that come in squares. Okay? Now, is it true that in art and in architecture that it was known that this was the best looking shape or not? Because the Greek Parthenon, a famous structure, has the golden rectangle all the way through it. And then this golden proportion even shows up some places in music. Okay? Beethoven, don't know if it's his 5th or his 9th. Which is the one that goes ba-ba-ba-bum, ba-ba-ba-bum, ba-ba-ba-ba-ba-ba-ba-ba-ba-ba-ba-ba-ba-ba. You know that one? Is that his 5th or his 9th? I'm not sure which one it is. So Beethoven introduces that main theme in bar 1 of that symphony. He then plays around with it for a Fibonacci number of bars, and only after doing, who knows if it's 233 or 89 or whatever it is, after playing around with that main theme for a Fibonacci number of bars, he then reintroduces the theme for the second time and then takes a Fibonacci number to finish his piece. Did he feel like the timing proportion would sound the best? It's one of his famous pieces. Anyway, so those are the Fibonacci numbers, and they're connected in Pascal's triangle. But our focus is on Pascal's triangle. So we look at some patterns, and if you turn to the next page, you could write row 9. We'll skip that because that's easy. But if you calculated 4 choose 0, you would get 1. 4 choose 1, you would get 4. 4 choose 2, you get 6. 4 choose 3, you get 4. 4 choose 4, you get 1. So Pascal's triangle is also connected to our combinations. The combinations match up with the with Pascal's triangle. Okay. And what we're going to look at in the next thing and relate it to Pascal's triangle is binomial expansion. Binomial expansion means, you've done this before, right? What's a plus b squared equal to? Well, yeah, that's true, a squared plus b, but a plus b squared, if you FOILed it out, you would get a squared plus 2ab's plus b squared. Okay? What happens if you did a plus b to the 1? That's really boring. You would just get a plus b. What happens if you do a plus b to the 0? You would just get... What do you think you're going to get if you do a plus b cubed? You would get 1a cubed plus 3 a squared b's plus 3 ab squareds plus 1 b cubed. I need you to fill out, looking at the pattern, a plus b to the 4. This is important, yes. You could write this on, or you could look on page 739, because it's basically there with x's and y's. Whew. So how do I figure out there's a 1 to start with? Because that's Pascal's triangle. Then there's going to be an a to the 4 plus the next number on Pascal's triangle is 4. 1 less a and now 1b. Notice the variables, there's always 4 of them. And then 6, 1 less a, 1 more b. And then 4. Now the idea, right, when you multiply a plus b times a plus b times a plus b times a plus b, why is this connected to combinations? Okay, I'm going to tell you, but if you wanted to do some sort of fancy foiling, well, you could have the first one's all multiplied together. You could have this one times this one times this one times this one, this one times this one times this one times this. There we go. This one. There we go. Yeah. So you could have like a if you had an acronym that helped you memorize how to do this. Basically, what happens when you multiply all of these things together is that you're always choosing one thing from each thing when you multiply them. And you have 4 a's and you had to choose all 4 of them. There's only one way to do that. But if I'm trying to get 3 a's and 1 b, how many ways could I choose the b to be in there? I have 4 b's. I choose one of them. 4 ways. How many ways could I choose 2 of the b's? There's 4 b's. I choose 2 of them. And then, of course, whichever 2 b's I choose, the other a's would have to go with that. And so that's why there are 4 choose 2 or 6 a squared b squareds in the expansion. Of course, you could multiply it out slowly, but what we're going to do in the next part is we're going to look at this pattern and use it to multiply ones out that have numbers much larger than 4, like 5.